Hello everybody and welcome to the second session of ICFP 2020. You're joining us on YouTube, and registered participants for the conference can also join us in chat on the Clouder system, and also, if they want to, join a live Q&A with the authors after the talk. And so the first talk for the session is going to be Achieving High Performance the Functional Way, and it's going to be presented by Bastian Hagedorn.
Hi, this is Bastian Hagedorn from the University of Münster, and I'll be presenting our functional Perl on achieving high performance the functional way. This one's about expressing high performance program optimizations as rewrite strategies. This is joint work with colleagues from the Universities of Edinburgh and Glasgow. Let me begin with asking the question why we care about high performance in the first place. And the answer is quite simple. We literally cannot afford not to, because apparently it costs about $250,000 to perform state-of-the-art machine learning research. And this high cost is mostly due to the long time required to train neural networks on parallel hardware. It gets worse when you translate the dollars spent into carbon emitted. So here, training this neural network released about 5 tons of carbon into the atmosphere, which is equivalent to driving 11,000 miles with a car. And just to show you how insane that is, here's a map showing a road trip from the north of Norway all the way down to South Africa, which corresponds to roughly 11,000 miles. So clearly, we need to find a way to reduce those costs, and optimizing a program to achieve high performance might allow us to significantly reduce the time required to, for example, train neural networks. So how do we achieve high performance? Here's a naive implementation of a matrix multiplication computation in CUDA, which targets GPUs. And if you know a little bit about CUDA and GPUs, I'd argue that this is quite easy to write and to understand. But unfortunately, this program is also not very fast. So for achieving the highest performance on modern GPUs, this simple program has to be significantly modified. So for example, here's an optimized version of the same computation, which achieves up to 3 orders of magnitude more performance. And if we compare this again to our road trip example and the carbon emitted, 1000x improvement barely allows us to drive 15 minutes on the highway. However, this manual way of achieving high performance requires some expert to sit down for quite some time and to optimize their program in a time-intensive and incredibly error-prone process. So another way to achieve high performance is what I call here the decoupled way, which was pioneered by a domain-specific compiler called Halide. And the key idea here is to decouple what is being computed from how it is optimized. So this allows a domain scientist to focus on implementing the computation, which can then be separately optimized by a performance engineer with a so-called schedule. And this way of achieving high performance is currently very popular, and there are many compilers following this approach. So this particular example here is taken from the TVM machine learning compiler, which is currently the state-of-the-art in generating high-performance machine learning implementation. TVM comes with a tutorial on how to optimize matrix multiplications for CPUs, and we'll take a closer look at that in a moment. So the TVM compiler uses both the algorithm and the schedule to generate an efficient implementation. So here, for example, we see the blocking version from the TVM tutorial, which applies some specific loop transformations. The best version presented in this tutorial is about 200 times faster than the baseline, but only requires to add a few more lines to the schedule. Well, at least that's the idea. So when you take a closer look at this schedule-based approach, you'll find a few problems. So one of the first few things you might find is that the algorithm and the schedule are not fully separated. Here, the schedule uses the same Python identifier that has been declared in the algorithm, and that simply means that both the algorithm and the schedule have to live in the same scope, and that hinders the reuse of the schedule for optimizing a different computation. The next problem is that there is no well-defined semantics for the scheduling primitives. So there is only a documentation online, and for some primitives, this is quite cryptic and basically requires knowledge of how the compiler internally implements the scheduling primitives. And finally, all scheduling primitives are built in, which makes them hard to extend. So typically every primitive like tile or vectorize represents a common optimization you might want to apply, but as soon as you need something slightly different, you're in trouble because there's no easy way to extend the set of exposed optimizations besides digging deep into the implementation of the compiler itself. And this is something we don't often want to do. So this is why with our functional Perl, we aim for a more principled way to describe and apply high-performance program optimizations. And specifically, we aim to separate concerns by expressing a computation at a high abstraction level only without changing them for expressing optimizations. We aim to facilitate reuse by defining optimization strategies clearly separated from the computations. We aim to enable composability by allowing to define both computations and optimizations as compositions of user-defined building blocks. We aim to allow reasoning by giving those building blocks well-defined semantics. And finally, we aim to be explicit and avoid all implicit default behavior of the compiler. And essentially, we argue that a strategy language should be built with the same standards as a language describing the computations. Now, let me show you the functional way of achieving high performance. And our approach follows the same idea of decoupling computations and optimizations, but we're using the well-established functional programming techniques to express both. So on the top left, we have a high-level program that is written in the functional programming language called RISE that is based on an ICFP paper from 2015. And on the right, you see an optimization strategy that describes how to optimize that RISE program. And this is written in Elevate, which is based on ideas already published in the late 90s. Our compiler then rewrites the RISE program based on the optimizations described in the Elevate strategy and eventually generates high-performance code. Our function in Perl is all about how to express the high-performance optimizations, typically applied manually or using the schedule-based approach, however, as composable rewrite strategies instead. All right, let's see how we do this, and we'll start by taking a closer look at Elevate, our language for describing the optimizations. The most basic building block in Elevate is a strategy, and a strategy is simply a function from some program P to what we call a rewrite result. And a rewrite result is simply saying whether the applied strategy succeeded, in which case it contains the rewritten program, or it failed, in which case it contained the strategy which failed. Rewrite rules are examples for very simple strategies, and you could, for example, go ahead and implement the typical map fusion rule for RISE programs as an Elevate strategy, as you see on the bottom. And this rule simply says that whenever you see a RISE program that contains two consecutive maps, you can fuse those maps and return the fused program. And if there are no consecutive two maps, then this rule is simply not applicable and it fails. For building more powerful strategies, we can combine rewrite rules in Elevate using several different combinators. So for example, the sequence combinator allows to apply two strategies in sequence. The left choice operator expects also two strategies, but only applies the second one in case the first one fails. The try combinator tries to apply the given strategy, and if it is not applicable, it simply returns the unchanged input program by applying the ID strategy. And finally, the repeat strategy allows us to repetitively apply the same strategy until it is no longer applicable. Now, what if we have the following situation? Here you see a RISE program that contains three maps. And if we now want to apply the map fusion rule we've just defined, there are two possible locations for fusing the maps. So we can either fuse the first two or the last two maps. With Elevate, you can precisely define locations in the AST using so-called traversals. So for example, the body traversal applies a given strategy at the body of a function abstraction node. And in this example, body map fusion would then fuse the first two maps as you've seen here. Similarly, we define traversals for the other nodes and could, for example, apply body argument map fusion for fusing the last two maps in this expression. And in the paper, we explain in more detail how to describe precise locations using these and other traversals. Sometimes it's not desirable to specify a precise path, but instead we might want to say something like, apply this given strategy at the first place you'll find. And this is what bottom up or top down do. So these traversal strategies traverse the AST either like from top down or bottom up and apply the given strategy at the first place where it's applicable and then stop. Another useful traversal is the normalized strategy, which applies a given strategy exhaustively until it is no longer applicable anywhere in the given expression. And in the paper, we define a few normal forms for Rice expression. And one simple example of one of those is the beta-eta normal form, which simply applies beta reduction and eta reduction as often as possible. Using those generic building blocks, we then try to implement TVM scheduling language and try to especially define elevate strategies that apply the same optimizations as described in the TVM tutorial, which we've mentioned earlier. So here's what the baseline version looks like. And for TVM, we describe the matrix multiplication using the Python API and use the default schedule to generate unoptimized code. For our function array, we describe the matrix multiplication computation using Rice and its function array primitives like map and reduce. And we define a separate strategy in elevate, which explain how to optimize this computation. And here we can already see that we have a clear separation between the computation and the optimization. More crucially, TVM's default strategy implicitly describes some way of lowering the program to executable code. And we don't really know how this is performed. With our approach, we aim to completely avoid implicit behavior and describe every transformation explicitly. So here we're simply saying that the dot product should be computed using a single statement by fusing the map and the reduce pattern similar to how TVM computes the dot product. This way we implemented each of the 7 differently optimized versions. And in the paper, we describe, for example, how to implement TVM's built-in tile optimization as a composition of only a few rewrite rules and the combinators and traversals we have just seen. Also, our functional approach allows us to define the different optimized versions as reusable strategies. So here, for example, we define the loop perm strategy, which we will reuse in the following more optimized versions. This is the most optimized version implemented in both TVM and our approach. And here you can see that we are able to reuse and to build upon the loop perm strategy, whereas in TVM, we always have to describe the whole optimization from scratch because we cannot easily define our own abstractions. One crucial problem is also that the TVM algorithm has to be changed a few times during the tutorial because the scheduling language is not powerful enough to express all desirable optimizations. Our approach with Rice and Elevate does not require us to do so, and we use the same Rice matrix multiplication that is optimized by 7 different and separate Elevate strategies. To evaluate our approach, we looked at 2 things. So first, in the first experiment, we simply counted the number of successful rewrite steps per versions, which you can see here. And since the baseline version does not perform any interesting transformations, it only requires a few rewrite steps. But as soon as we're performing actual program optimizations, we reach about 45,000 and later up to 62,000 separate rewrite steps. And this shows that our approach is scalable because we were able to define the complex TVM-like optimizations by simply composing a few rewrite rules using Elevate. Also, performing this many steps took less than 2 seconds per version on a regular notebook. So this is no bottleneck. Obviously, we also wanted to see if the performance we achieve with our function array matches the performance achieved by the TVM compiler. And here you see the performance achieved for each of the 7 different versions. And you'll find that we are able to achieve a similar trend, which means that our Elevate strategies encode the same high-performance program optimizations as applied by the state-of-the-art TVM compiler. And if you would like to find out more about a functional way of achieving high performance, simply contact us or have a look at our paper. And with this, I'd like to end the presentation and mention that you can find all our implementations online or in the artifact. Thanks for your attention.
So thank you, Bastian. So for anybody who's wanting to join the authors for the live Q&A, you can click on the link that's in the Slido page for this talk. Our next paper in the second session of ICFP 2020 is going to be stage selective parser combinators, and it's going to be presented by Jamie Willis and Nick Wu.
Hello, can you hear me?
Hello, yeah, I can hear you.
Nice, I can hear you too.
So I don't know if we've met. My name is Nick Wu. I'm from Imperial College London.
Oh, hey, I'm Jamie Willis. I'm also from Imperial.
Ah, what a coincidence. It's strange doing an online conference with pre-recorded videos, isn't it?
Yeah, ICFP's format is interesting this year. I wonder if anyone's made the most of it with their presentations somehow.
Indeed. So what are you working on?
I've been working with parsers.
Ah, nice. I'm a big fan of parser combinators.
What are those?
Oh, well, they're a way of building a parser that follows the structure of a grammar closely by treating parsers as first-class values and building larger parsers from smaller ones.
Right, can I have an example?
Let's look at the BNF for a language that recognizes strings of characters. Let's suppose that they're non-empty. So here's some code. The non-terminal alpha is the choice of letters from A to Z, and alphas consists of one of those, followed either by more alphas or by epsilon, the empty token.
Okay, so how do you actually write the parsers then?
Right, and so in Haskell, alpha is a value of type parser char, since it parses a character, and here we simply give the alternative between each of the chars. The alphas parser returns a list of chars by first parsing an alpha, and then appending it to the result of more alphas or just the empty list.
Right, so how does that strange cons thing work?
Okay, so parsers are applicative, so we can lift normal functions and constructors like cons so that they can work on parsers. So here the pure cons just makes a function work at the parser level, and then the app, which is the star, will ensure that px is parsed first, followed by px's, and then it's put together with cons.
That doesn't seem like something you could execute.
Well, if you want to actually run one of these parsers on an input string x's, then you use the run parser function that will take the string and return the parsed result if it can.
Right, so those combinators seem really verbose. I usually just use eBNF like this, where you'd use a character class and a plus, and it gets rid of a lot of the bloat.
Oh yeah, sure, that makes sense. Well, you can also do this with combinators as well. Here's what you do with alphas. We're using one of, which will take one of the A to Z in the range as you've done, and the plus says that you simply want some of those.
Ah, that's neat. Okay, so how are one of and some implemented?
Well, they're also in terms of simpler combinators. One of is in terms of the primitive satisfy, and satisfy takes a predicate and accepts an input character that satisfies it. For one of, we simply want it to be an element of a given list C's. Some can actually be implemented in terms of what we've seen so far. Can you see how?
Sure, let me see. I think if I took the alphas example, I could reverse engineer it. So I guess if I factor this alpha out, then that would give me some. So I'd replace alpha with some px and then alphas with some px.
Yeah, that's right. And you could furthermore factor out what's inside the brackets to have both an implementation of some and many.
Right, so if some is the eBNF plus, then many's the star? But using parser combinators surely has a performance impact.
Right, yes. So there's definitely some overhead to using these kinds of combinators. But on the other hand, if you represent these combinators as a deep embedding, where the combinators are all data constructors, then you can do things like grammar analysis, which is driven by various laws, such as the applicative and alternative laws.
I guess you could optimize it that way. I think it's easier to understand performance by thinking of an underlying stack machine.
What do you mean?
Well, you can represent parsers as a machine with one stack for intermediate results and another for handling failure. And then you pass by executing instructions that interact with these stacks when they're given some input stream. So I guess we'll take your previous parser as an example. So here it would be.
Whoa, is that really still Haskell?
Yeah, sure. This is clearly just a recursive machine reading alphabetical characters, setting up failure handlers before recursing again and combining elements of the stack. What's there not to understand? Isn't this how you were taught to use Haskell?
Well, I think you'll have to go a bit slower than that for me.
Right, sure. So just read those dollars as semicolons in your favorite imperative language. Then alpha is similar to yours. It's just an instruction that verifies a predicate on the next input token and then continues with another instruction K. And alphas performs alpha and then leaves its result in the stack. It enters a catch block to handle any failure. And inside this block, alphas is ran again, which leaves its result in the stack too. and the two results are combined with lift 2 cons. Then things are free to carry on with the next instruction K. But if failure happens, then the first few instructions of that second block before the case check that the input hasn't changed since starting the catch. And the case instruction then uses that information to either fail or combine alpha with the empty list before continuing with that same K.
Oh, I see. So your representation is much more explicit about control flow than mine.
Yeah, analyzing the control flow in my machine is quite straightforward. I think this is a lot more complex in your case.
Yeah, that's true. The control flow for the grammar isn't obvious at all until you start looking at something like derivatives.
Okay, hang on. I think I can see what's happening here. The representation that I have is the same as yours. It's just been transformed into CPS, continuation passing style. That's what makes the control flow explicit. Basically, each instruction takes as an argument the next instruction executes, and this is interpreted by passing around two continuations at runtime, the good continuation and the bad one.
Of course. So if you can convert between the two representations, then you'll be able to get both the high-level optimizations and grammar analysis of my approach, and the low-level optimizations and control flow analysis of yours. You get the both of both worlds. There's a problem, though. The machine you showed me before is untyped. How can we convince ourselves that the translation is working properly? My combinated tree is fully typed.
Well, my stack represents what's already been computed, right? I guess in your world that corresponds to combinators that have already been executed, and each combinator will push exactly one thing to the stack if it's successful.
So what if we can propagate my type information into a type level stack? Here, let me show you what I mean. So Halt is basically produces a machine that expects an A on an empty stack and returns that A.
Wait. How does that get implemented?
I see. You just use an H list. It's a heterogeneous list so that the values can have different types. The types of each element are kept in a type level list, and this list is the same as the one that will appear in our instruction types.
Oh, right. Okay, thanks for that. Carry on.
Right. Where was I? Okay, so push takes an X and a machine that expects X and X's and produces a machine that expects just X's. And pop takes a machine that expects only the stack X's and produces a machine that expects an X on top of the stack X's.
Right, I think I see. So the continuation of machine expects a stack of a certain type, and then the instruction will adapt that stack to fit. I guess that compiling a combinator to a machine means taking a machine that accepts the result and makes progress towards some final goal. So it's something like this then. Compile sub will take a parser returning an A, and then a machine that accepts that A along with some X's, and then we can build a machine that requires just that X's in order to continue. And the final continuation is going to be halt. It takes the one element on the stack and gives it back.
Right. So how would you translate combinators? So for example, the pure, which has type A to parser A, and app, which has type parser A to B to parser A to parser B.
Oh, easy. Something like this. So for pure, that's just the push instruction, right? With some M that will continue on afterwards. And then for app, we just need to compile PF, and then we'll compile PX. And after that, we combine the two results that are on the stack with function application using lift2.
Ah, neat. So, but what about the and then variant of app, where you discard the first argument rather than applying a function, something like parser A to parser B to parser B?
Oh, sure. All you need to do is pop after passing the first result. So you compile P, then you pop that result off, and then you compile Q, and then carry on with M.
Oh, neat. So I can see how this might work out. You know, now that we can see this as using CPS, it kind of reminds me of some work that my PhD student, Matt Pickering, has been doing lately on staging. Actually, there's a paper being presented at the Haskell Symposium about it coming up in just a couple of days.
Sorry, what's staging exactly?
All right, well, so staging is a form of metaprogramming where you can perform work on statically known results ahead of time, leaving only dynamic information at runtime. It's basically giving you fine-grained control over evaluation in your compiler. In our case, the shape of the machine for a parser and its combinators is static. In other words, it's known by the compiler.
I think I understand. So this means we can perform that translation from combinators to machine and evaluate most of it at compile time. I've heard of template Haskell, but that's untyped, right? It seems a bit of a waste of all the hard work we did to make everything typed.
Right, indeed. And I guess you haven't heard of type template Haskell. Unlike template Haskell, where you build ASTs, with typed template Haskell, you can only work with well-typed terms, which ensures that the process is safe. For example, if you have some term E of type A, then it can be quoted to get the code that represents E at runtime, quote E, which is of type code A. If you want to splice or run some code, you simply use the anti-quote by adding a $to the front. So for some code C of type code A, splice C gives back a value of type A.
Oh, so all I have to do is add code to the parts that are going to happen at runtime?
Yep.
Okay, so let's have a look at the machine state then when it's interpreted and see what we can uncover. So quickly, let's look at how we actually evaluate the machine normally with the run machine function. So we're going to provide some machine state gamma to the eval function, and that's going to interpret the meaning of each instruction in M. So all gamma is just our heterogeneous operand stack along with a return continuation for recursion, a stack for failure handlers, and the input X's itself. And so the bit that we can actually stage about this would be the eval function, because it's the machine that's known at compile time, right? So if I just add code around it, then that makes the function from machine state to final value part of code, and that will be done at runtime. And you can break this into a compile time function that takes code and returns code. That's fairly straightforward. But we should be able to do more than this, right? So the machine state gamma is always the same shape. So we should be able to get rid of that at compile time too. So if I push the code into the gamma, then we can ensure it only exists at compile time. Yeah, so at runtime, we'll produce a function with 4 arguments, 1 for each component, but the actual record's gone. But surely there's got to be more we can do now.
Well, the fact that HList in ops has the type X's implies that it must have the shape that we can know at compile time. And that's determined by the instructions also known at compile time. So you could push the code inside the HList.
I see. So if I map the code over the values in the HList, then the HList itself is only going to exist at compile time, and the values exist at runtime. And I guess that the structure of the handler stack is the same. It's determined by the instructions as well. So I guess we can operate with that list at compile time too. So with all things considered, I guess the only thing we don't really know at compile time is what the input is, and specifically what each continuation is at any given point. Everything else is gone.
Exactly, and that's why we like staging so much.
Awesome. So here's what the stage evaluation for push and halt might look like then. So halt will take the operand stack out of gamma and extract that top element and splice it into some code that builds a just for that value at runtime. And eval push, there aren't actually any quotes in the body at all, so it must purely happen at compile time. That's really cool. So I guess let's push our original example through this mechanism and see what code it generates. Wow, this is quite cool. So I guess we can see that none of the abstractions from the combinators of the machine are here at all. It's literally just a couple of functions taking as argument this good continuation and the bad continuation, and some input, and it'll all thread it round together. This is awesome.
Yeah, it is. It's really good. But there is a small problem. Most parser combinators, such as Parsec, have this combinator called bind, which is usually used to implement context-sensitive parsing. The stuff that was previously parsed can influence the grammar that is used to parse the rest. The trouble is that I don't think this can be staged.
Ah, that's a pain. I mean, do you really need to create a whole new parser that we can't inspect? What sort of things do you actually use it for?
Well, I suppose most of the time the grammar is static and bind is used to select the part of the grammar that's already known.
Oh, well, we've already seen an operation like that, right? It was case. So both of the outcomes are known statically, but you don't know which branch is taken until runtime.
Interesting. I wonder if this corresponds to Markov's work on selective functors. It seems to behave similarly to his branch operation, which arbitrates between two branches depending on a coproduct.
Yeah, I think that sounds about right.
Great. So if we give up bind and work with selectives instead, we can use staging, and that makes things really fast.
Let me quickly whip something up and we can see how it performs on some benchmarks I made earlier.
Wow, kids these days are really fast at programming things.
Ah, perfect. It worked first time. That's unusual. Must be those strong types. Right, here's the results. So this graph is showing us that actually compared to the other combinator libraries, we're about 3 or 4 times faster, and we're even beating Happy. That's a parser generator library.
Wow, that's really good performance.
Yeah, this is great. Maybe we should write a paper about this.
Well, you're pretty good at coding things quickly, and I'm pretty good at writing papers quickly, so here you go. Cool. I'm going to stop recording now, I think.
Okay, thank you, Jamie and Nick. So if you want to join the authors for a Q&A in the New York time zone, then you can click on the link in the Slido room. Hello and welcome back to the second session for ICFP 2020. And our next talk is going to be kindly bent to free us, and it's going to be presented by Gabriel Radanne.
Hi everyone, so I'm Gabriel Radanne and I'm going to talk to you about memory and safety for a little while. Here is a report provided by the Chromium team about high severity security bugs in Chromium, and you can see that almost 2/3 of the bugs in Chromiums are memory related and 1/3 of the bugs are simple use after free errors. So you could say, okay, Chromium is written in a mix of C and C++, and surely this bug don't happen in high-level typed languages, right? Let's write some OCaml code. Here is a small example of code where we open a database, we write a grade, database of grades, we write some grade in the database, the mass grade, we close the database, then we try to read the literature grade and print it. So the OCaml type checker will happily type check and compile this program, and later on we will have a runtime error. So there are various ways to deal with this kind of errors, and today I'm going to present AF, which is an ML-like language that prevents precisely this kind of error. So here is the same program written in AF. It looks very much like the ML program, the OCaml program from before, except this time when we reach the last line, then the type checker will refuse at compile time this program. So we have a few specificity in AF. The first one is that we use kinds to determine usage. So here the grade database is of type database, and the database is of kind linear, and so this resource must be used linearly, and when it's closed you can't use it anymore. On the contrary, here we have the math string, and string are unrestricted, and so you can use them in unrestricted fashions. Furthermore, we have borrows, so as present in Rust and other languages, borrows allows to do imperative programming very conveniently, and that's why we use them here. Finally, a final specificity of AF is that we have complete type inference. So before I used a type annotation here to simplify, to make it easier to read, but I don't need to. Here, type is completely inferred by the type checker. So to present AF, I'm going to go through various of its features, and I'm going to start by linearity. So as I said before, kinds determine usage. We have three kinds. Linear, a resource must be used exactly once. Affine, a resource must be used exactly at most once, so 0 or once. And unrestricted, the object can be used arbitrarily many times, from 0 to infinity. Here are a few examples. We have a database type of kind lin, a string type of kind unrestricted. We can also have parameterized kind, so for example a list as the kind of its content. If we have a list of database, then it must be used linearly. If we have a list of string, it can be used unrestricted, in an unrestricted fashion. To use this kind of parameterized kind, we also have kind constraint. So here we have the type function create list, which takes an element and replicates it multiple times to create a list. Since the element is going to be replicated, then naturally its content must be unrestricted, and that's exactly what this constraint says. Finally, we also use subkinding. So un is smaller than af, which is smaller than lin, and that means that if a function only expects linear objects, we can pass it unrestricted objects. And the reason is that if something can be used in unrestricted fashion, in particular it can be used linearly. This is the base of our language, and we're going to use it to build up everything else, and in particular functions and captures. So here's a piece of code where we open the grade database, then we create a function that logs some message and then close the database. As you can see, we have a capture here. The log and close function captures the grade database. And grade database is linear. It must be used exactly once. And so the log function must also be called exactly once. If we ask the AF type checker, it's going to give us this type, string, arrow annotated by lin, and unit. And the annotation on the arrow indicates indicates the usage mode of this function. It indicates that log and close must be called exactly once. A fair warning, to make everything clear, this annotation does not say anything about the argument. Here, the argument is of type string, so it's unrestricted. You can do whatever you want with it. The arrow, and in particular this linear arrow, is not a lollipop from linear logic. It only says something about the function itself. Alright, so we can do nice functional programming with all this. Let's look at imperative programming, and for that we need borrows and regions. As in Rust and other languages, a borrow is a temporary loan of a resource A, and we have two types of borrow. Shared borrows are for observing the resource, and exclusive borrows are for modifying the resource. Here is an example of a correct use of borrow. We start by looking up two grades concurrently, so this is a read action, so we use a shared borrow for observing the database. Since it's shared, we can look up two things at the same time, concurrently, and in particular the kind of this is unrestricted. Once we are done with looking up these two grades and making their average, we can write in the database using an exclusive borrow, and exclusive are, as I said, exclusive, and they have in particular the kind affine. So there are a few rules to use these borrows. The first rule is that you cannot use a borrow and the resource itself at the same time. Here, the f function is called with the resource and a borrow, and that's not allowed. The type checker will reject this. A second rule is that we cannot use an exclusive borrow and any other borrow. Here I have an exclusive borrow and another borrow, and the type checker will again reject this. Finally, a borrow must not escape. Here we have a declaration of a database and then a pair composed which contains a borrow, and then we try to leak the borrow while the database is still captured inside the function. So this is not allowed because the borrow is escaping its region, and here is the region delimiting the borrow. So the regions are almost lexical scoping with a few tweaks, and the way we check for this kind of escape is by using the indexed kinds. So before I said the kinds were unrestricted, affine, and linear. Actually there are a bit more. They are indexed by their nesting, and here the grade, the borrow of the database is in the second nesting, so it's annotated by un2, whereas the region around it is at the nesting level 1. And so we will simply check 2 is bigger than 1, so the borrow cannot escape. And the type checker will again reject this. Alright, so we have borrow, we have closure, we have functions, we have linearity. Let's put everything together. Here is the API for the database that I've used since the beginning of this talk. The type database is of linear kind. We have the find function that takes a borrow with its kind and takes a string and returns an integer. We have the add function that takes an exclusive borrow, a string, an integer, and returns unit. And since the functions are purified, you can here database borrow is captured later on, and so the functions are annotated with the kind that is captured here. Here is a simple use of this API, as I said, which was presented before. So we have two concurrent lookup, grade DB, of the grade DB of two grade, math and comp-sci, and then we compute the average. We can factorize a little bit the lookup aspect by creating a grade function that captures the database and look up the topic or the subject of the grade. And here we repeat the argument, subject and subject. So we can simply partially apply the function and it will compute the borrows and the kinds accordingly. And finally, we can even go further and use some functional abstraction to pull the function computing the average outside by taking a list of subjects and applying a partially applied function in list.map and so on and so forth, and use high-order functions as we would want to in a functional language. The type checker will annotate the region as we would expect. Here are the disjoint region for the shared borrow and the exclusive borrow, and they are properly disjoint. Finally, as we said before, we have no type annotation. So even if I used the average, even if I lifted the average function out, I still have no type annotation here. We have complete type inference. All right, so let's look a little bit under the hood at inference and constraint. The first step is to elaborate the region by using the information provided by the position of the borrow, the scopes of the borrow, and the borrowing rules I presented, which allow us to completely determine the biggest region we could use. The second step is to generate constraints which will encode type, linearity, and borrowing checks, and to check that nothing escapes that shouldn't. This constraint system is custom to encode the rule we want and based on HMX. Finally, we solve the constraints using a custom algorithm that we provide, and we obtain principal type schemes for all the functions in our program. So this principal type scheme can sometimes still be a little bit complicated, and so we use subkinding rules with positive and negative position to simplify the type further down. Alright, and so we obtain finally the simple type schemes. So to summarize, I presented the F language. A prototype is available at this address online. We provide linearity, closure, borrows, and region to provide good support for both imperative and functional programming. We support managed and unmanaged object and principal and type inference, which is something very novel for languages that support borrows. The downside is that so far we do not support real flow sensitivity. We can emulate various bits, but it has no proper support. And we do not have yet a concurrency story, so that's something we are working on. In the paper, you can find many examples to show that we can indeed support many types of programming, both functional and imperative. On the theory side, we provide a syntax-directed type system for AFA, or to encode into an ML-style type system. We provide a formal account of the semantic and its proof of soundness, and an inference algorithm for AF, which provide various novel contribution, in particular an extension to HMX, novel constraint system, and its constraint algorithm and proof of completeness. That's all I have. Thank you very much.
So thank you, Gabriel. So if you want to join the author for a live Q&A, click on the link in the Slido room for this paper. Hello and welcome back to the second session of ICFP 2020. And our next paper is going to be sealing pointer-based optimizations behind pure functions. And it's going to be presented by Daniel Salzman.
Hi everybody, my name is Daniel Salzman from Microsoft Research. I'll be presenting joint work with Simon Hudon from Carnegie Mellon and my colleague Leonardo Demura from Microsoft Research. Our paper is titled Sealing Pointer-Based Optimizations Behind Pure Functions. Now, functional programming really shines for interactive theorem provers for many reasons. It's easy to encode terms with inductive types, and this is actually surprisingly cumbersome in C++. It's easy to traverse terms with higher order combinators. For example, a function, easy to write functions that replace subterms of terms or find subterms matching patterns. And it's easy to backtrack using persistent data structures. So we can just snapshot the world, try tactic 1 in that world, and if it fails in constant time and no extra programming effort, we can just roll back the world to the snapshot before we started tac 1 and then try the second tactic in it. And as we would expect, most interactive theorem provers are written in functional programming languages. So Isabelle Hall is written in PolyML, Coq is written in OCaml, Agda and Idris are written in Haskell, and Lean 3 was written in C++ at great spiritual cost, but Lean 4 is being rewritten in Lean 4 itself, which is a functional programming language. But while functional programming shines in this domain, pure languages suffer a critical limitation that we call purity's Achilles heel, which is that traversing a term requires time proportional to the tree size of the term as opposed to its graph size, which causes exponential blowup in theory and in practice. And here's a little illustration. On the left, there's a term whose DAG representation has only 4 nodes, and in fact, has only 4 nodes in memory. But when you view it as a tree, it has 2 to the 4 minus 1 nodes. So exponentially more nodes in its tree representation than in its graph representation. And perhaps a surprising empirical finding is that terms with astronomic tree sizes are actually extremely common in interactive theorem provers. So it's well known that even basic operations can produce them. So unifying two terms where the function symbol has arity n can produce a term whose tree size is 2 to the n. But this is a somewhat contrived example. But in reality, terms are often the result of long chains of somewhat arbitrary user-written metaprograms or tactics. And at least in Lean's mathematical library MathLib, it's not uncommon for a proof that has only 20,000 nodes in its DAG representation to have over 2 billion nodes in its tree representation. And many performance issues in Coq and Lean, going back many years, have been the result of improper handling of such terms, despite having the needed impure tools at hand. Basically, the exponential blowup is so severe that if a single module ever traverses a term with insufficiently precise caching, it's very likely going to be a bottleneck. And now we can talk about our contribution. So we present a new way to, quote, seal the needed optimizations, the optimizations that you need to traverse terms in linear time. We show how to seal these optimizations behind pure functional interfaces. And here's the main idea. We start with a pure reference implementation of something that we want to optimize. We find sufficient conditions for a particular optimization to respect the reference implementation. We then create a new primitive that takes these conditions as preconditions using dependent types, and otherwise is given the nominal pure reference implementation. And then we just compile this primitive into the optimized version. And a simple meta-theoretic argument establishes that since it was proved, since the preconditions were proved, the optimization is sound. And we show how to do this for several common low-level optimizations, including pointer equality tests and even direct pointer address manipulations. And we show how to use these new primitives to traverse terms in linear time, which is the problem we set out to solve. So perhaps the simplest pointer optimization is just short-circuiting equality tests using pointer equality. And the idea is simple. If two terms x and y have the same memory address, they must be structurally equal. So you can skip the potentially exponentially expensive structural equality test and just return true. And the challenge here is that this optimization is only sound in general for reflexive relations. And the solution is somewhat simple. Allow the optimization for any relation that you can prove is reflexive. Which brings us to our first new primitive, which we call with pointer eq. And now with pointer eq takes two terms, x and y, of type alpha, and a thunk k that takes a unit type and returns a bool. And the precondition h is a proof that if x equals y, then this thunk k is going to return true. And then the overall primitive with pointer eq returns bool, and its pure reference implementation just simply evaluates the thunk. And now the compiler will treat this as opaque until reaching the low-level IR, at which point it will expand a call to with pointer eq to the following pseudocode snippet. It first checks if the pointer addresses are the same of x and y. If they are, it returns true. Otherwise, it evaluates the thunk. And the precondition h guarantees that this version respects the pure version by a very simple argument. Now, with pointer eq alone already can yield exponential speedups on pointer equal terms, trivially. But small deviations from pointer equality remove the benefit entirely. So this is an illustration of two terms that share, pointers share an enormous tower, but their heads are actually different. So they are not themselves pointer eq, even though their children are. So with pointer, a single call to with pointer eq will just see that they're not pointer equal and fall back on recursive structural equality. Obviously, what we want is to call with pointer eq recursively on the children, and we can do that. The construction is somewhat elaborate, but it's entirely mechanizable, requires no new primitives, and the paper goes into the details for those who are curious. Now we're almost ready to traverse terms in linear time. Consider the naive exponential time algorithm to evaluate a simple arithmetic term into a natural number. So pretend we have a term type that has two constructors, one and add. So we can just evaluate this into a net by mapping 1 to the numeral 1, and by evaluating add t1, t2 by first evaluating t1, then evaluating t2, and adding the results together. Now, we're going to show how to use with pointer eq, the recursive version, to build a linear time version of this algorithm. We need two additional components. We need constant time intrusive hashing, and we need something that we call sharing the common data, which I'll discuss shortly. So it's almost hard to believe, but even just computing the hash of a tower requires exponential time. But hashing, unlike equality, is a unary function. So in principle, we can compute it once and just store it somewhere, which brings us to this folklore trick, which we call intrusive hashing, which is to simply extend the term type itself to store the hashes of the terms as extra arguments to the constructors. So here, the third argument to add is an adder, which is just our type that represents hashes in this case. And we can write a fast constant time hash function that simply projects out this hash field. And we can write a smart constructor that internally calls the built-in constructor, but will compute the hash automatically using the fast hash on the children. Now, Lean4 has reference counting and destructive updates. So we can actually use imperative hash tables and get the desired expected big O of 1 lookup times. But if your language does not have this feature, then you can still use functional or persistent hash tables, and then all of the same constructions apply, but every time we say linear, it really means quasi-linear for you. Now, the semi-naive traversal we call eval fast eq fast hash, which is to use the recursive with pointer eq test for the equality, and to also cache using the constant time intrusive hash and a hash map. Now, this is already linear time on this example, strictly because of the recursive with pointer eq, and because of the intrusive hash cache, it's also linear time on this example in expectation, because with high probability, the hashes are going to be different, and in the small chance that they're the same, they're very unlikely to be the same again for the children, and so on. But this semi-naive algorithm is still exponential time on this example, where we have two structurally equal terms that are pointer disjoint. And this brings us to sharing the common data. So with low-level pointer manipulations, we can, quote, share the common data in linear time. And what we mean by that is to take a term like this that has multiple subterms that are structurally equal but pointer disjoint, and simply share the common data or compact the term and produce the term such that equality implies pointer equality of all subterms inside the term. And now in the paper, we introduce additional primitives that allow writing pure versions of this procedure from first principles in linear time. But lean, as part of the lean runtime, we already have a high performance version of this procedure that applies to objects of any type. So there's no additional trust required to simply expose it. So we present a new primitive, share common, that is just the identity function, whose reference implementation is just the identity function. It actually takes no additional preconditions, but under the hood, it's going to share the common, use the runtime support to share the common data inside X. And finally, we have a robust linear time traversal, which we, to be overly pedantic, call eval fast-eq fast hash share common. And the idea is simple. We first share the common data, which takes linear time. And then we call eval fast-eq fast hash, which is linear time as long as the data has been maximally shared. And our motto in general is if terms are equal, they should be pointer equal. And they will definitely be pointer equal after share common. And if terms are not equal, their constant time hashes should not be equal with high probability. Now, the paper covers many extensions and alternatives to this approach. I'll go through a couple examples very briefly. So we can have a pointer equality test without requiring reflexivity as follows. Here's a primitive with pointer eq result that takes two terms x and y. And instead of a func k, it's a continuation that gets to see an optional proof that x equals y. But instead of returning a Boolean, it returns an element of any type beta. And now the precondition we need is that no matter what proof we give it, or what optional proof we give it, this continuation is going to return the same value. And the reference implementation just calls it on none. But at runtime, if x and y are pointer equal, we call it with the proof of reflexivity. And we can also support direct pointer address manipulation with the new primitive with pointer adder, which takes a term x, whose address we want to inspect, and it takes a continuation k that is going to look at that address, and again, return an element of an arbitrary type beta. And the precondition we need here is that no matter what address we give k, k returns the same value, and then the reference implementation just evaluates k at an arbitrary value, 0, whereas the optimized version will evaluate k on the actual memory address of x, and the proof very trivially implies that the optimized version is functionally indistinguishable from the pure reference implementation. Perhaps the surprising part of this is that this precondition isn't too restrictive. And we show in the paper that indeed we can do many, many sophisticated constructions using with pointer adder. And in fact, combining with pointer eq result and with pointer adder, we can implement pointer caches from first principles, and we can implement share common from first principles, and so forth. But we recommend the fast-eq fast hash share common approach in general. It gives very good performance in all our use cases in practice. It's simple, and the other constructions are significantly more elaborate for very little payoff. And thank you. That's all we have time for today.
Right, thank you, Daniel. So if you're interested in joining the authors for a live Q&A and you're in the New York time zone, then click on the link in the Slido page for this paper. Welcome back to ICFP 2020, where the next paper is going to be Effects for Efficiency, Asymptotic Speedup with First-Class Control, and it's going to be presented by Daniel Hillestrom.
Hi, my name is Daniel Hillestrom, and I would like to tell you about some recent work I've done with Sam Lindley and John Longley on how the presence of first-class control in a language can speed up implementations of some programs. I'll dive right in. The purpose of this work is really to explore space. The space I have in mind here is the design space of programming languages. When studying the expressiveness of some language feature, like first-class control, it is customary to consider a language with the said feature, and then the fragment modulo that feature. Then we can pose questions along different dimensions, such as computability, complexity, and programmability. However, any such question is really only interesting if the setting involves higher types, because to a fair approximation we can regard all reasonable languages with first-order types as being equi-expressive. So, in this work we are in the realm of higher types, and we show that in this realm the presence of first-class control can improve the asymptotic runtime of some programs. To show this, we consider the generic count problem, which asks us to implement a third-order function satisfying this type signature. Let's unpack the type. The first-order function parameter is called a point. It is a functional representation of a Boolean-valued vector of size n. The second-order parameter is a predicate function, which operates on points. It is an encoding of some search problem, and it yields true or false depending on whether it is satisfied by its provided point. Finally, any faithful implementation of this type signature ultimately returns the number of points satisfying a given predicate, or, in other words, it counts the number of times a given predicate returns true. We fix our base language to be simply typed PCF and extend it with effect handlers. Our concrete choice of control operator is not essential. Any first-class control operator will do. However, effect handlers do provide a particularly structured form of delimited control, which makes them convenient for the purpose of this work. Then we first show that there exists an implementation of the generic count in PCF with effect handlers, whose asymptotic worst-case runtime behavior is 2 to the n. Then we show that every implementation of generic count in pure PCF has at least asymptotic runtime behavior n2 to the n. That is to say, there exists a strict asymptotic efficiency gap between PCF and PCF with effect handlers due to the presence of first-class control in the latter. In this talk, I will not provide you with the actual proof of this. Instead, I will aim to give you the intuition for why this result is true. I will elaborate a bit on our methodology. We impose one important rule, namely that the type signature of generic count is fixed. That is, no implementation in PCF or PCF with effect handlers is allowed to change the type signature of generic count. A consequence of this rule is that it's not possible to translate PCF with effect handlers into PCF, say by way of an interpreter or CPS translation. This way, we really get to study the essence of the power provided by effect handlers. Moreover, this rule is also reminiscent of the restriction that programmers are faced by every day when they program against an interface, so we do consider this to be a reasonable rule. With this in mind, let's look at the following example predicate called EX and its induced computation tree model. The predicate takes a point as input and applies this point to 0 or queries the 0th component of the point. This is reflected in the tree model by the first interior node, which reads $0. I'm using the question mark prefix here to denote invocations or queries of points, and I'm using an exclamation mark prefix to denote answers or return values of predicates. Now note how the structure of the computation tree coincides with all the possible control flows of the predicate. Let's consider a concrete evaluation of this predicate. Suppose we apply it to a point whose 0th component is true, first component is false, and second component is true. Evaluation begins in the predicate and eventually occurs the 0th component of the point, which is true, meaning that we will take the left branch down the tree. This corresponds to continue with evaluation of the then branch in the predicate. Eventually, the predicate will query the first component of the point, which is false, meaning we'll take the right branch down the tree. And then at some point, the predicate will query the second component, which is true, meaning that we take the left branch down the tree, and we now hit a leaf node with the answer true, meaning that for this particular point, the predicate will yield the answer true. Now, this particular predicate belongs to a certain class of predicates that emit canonical models. We call such predicates instandard. A tree model is instandard if it is a perfect binary tree of height n. In addition, we also require that the tree contains every query and that no subtree repeats any query. We say that a predicate is instandard if its model is instandard. For example, the predicate EX is 3 standard. For the initial analysis, we restrict our attention to instandard predicates. This restriction serves to simplify the analysis, but it also provides us with an instance where the efficiency gap between PCF and PCF with effect handlers manifests as clearly as possible. This restriction enables us to give a crisp implementation of generic count with effect handlers. Okay, let's consider how one might go about and implement generic count with effect handlers. First, we need to take the predicate as input, and we have to apply this predicate to a point. We represent this point as the invocation of an abstract operation called branch. The only thing we know about branch is that it's going to ultimately return a Boolean value. In order to give an interpretation of branch, we must wrap the entire computation in a handler. A handler consists of 2 parts. A value clause that tells us what to do with the return value or the answer of a predicate. So if the answer is true, then we're going to return 1, and if the answer is false, we're going to return 0. Then the second part is an operation clause, specifically a clause for the branch operation, which in addition to giving access to the payload, also gives access to the continuation of the branch operation inside the predicate computation. This is a first-class entity, and what we do is we invoke the continuation with true first, and then we invoke it with false subsequently, and we sum up the result of those 2 invocations. Now, let's consider a concrete evaluation of fcount applied to our example predicate. The first thing that happens is the predicate queries the Selective component of the point. This query causes an invocation of the branch operation. This invocation causes control to transfer into the branch clause in the handler, where the first thing we do is we resume the continuation with true, meaning that we descend down the left branch in the tree. Now, when the predicate queries the first component of the point, the very same thing will happen. Another invocation of branch will occur, causing control to flow into the branch clause in the handler, where we resume the continuation with true, so we descend down the left branch again. We repeat the same argument when the predicate queries the second component, so we descend down the left branch. Now we find ourselves at a leaf node, meaning that we invoke the value clause in the handler with the answer false, meaning that we return a 0. At this stage, the handler is going to backtrack to the most recent query and apply the continuation to false, taking us down the right branch in the tree. Now we find ourselves again at the leaf node, so we're going to invoke the value clause, but this time with the answer true, meaning that we'll return a 1. The handler is now going to sum up the answers that it got in this subtree, which is 1, and then it's going to backtrack to the most recent query, and then the pattern repeats, so it's going to resume the continuation with false, and then subsequently with true. So, backtracking here ensures that every edge in the computation tree model is being visited exactly once. So if you generalize a bit, this means that computation involves big O of 2 to the n steps. Now, in PCF without effect handlers, there is no mechanism for backtracking of a sharing computation. Therefore, every generic count function must restart computation for every point. Let me try to illustrate what this means. Let's consider some generic count function applied to our example predicate. And let's for simplicity assume that this generic count function visits the nodes in the computation tree in depth first order. The first thing that happens is that the predicate queries the Selective component of the point, which returns true, meaning that we descend down the left branch in the tree. The same thing happens for the first component and the second component. And so we find ourselves at the first leaf. From here, there is no quick way to get to the second leaf, because there is no backtracking or any means for sharing computation. So the generic count function has to go all the way back up and construct a second point that represents the path to the second leaf, meaning that we'll have to repeat some work along the way in order to finally arrive at the second leaf. And here the situation is the same. In order to get to the third leaf, we must go all the way back up, construct a third point that represents the path to the third leaf, repeating work along the way in order to finally arrive at the third leaf. In general, the generic count function will have to construct endpoints in order to visit each of the leaves. This means that computation involves at least n2 to the n steps. Some might object to PCF as a choice of base language, because it lacks characteristic features found in, say, industrial strength languages. However, as we show in the paper, the efficiency gap remains even under extensions to PCF. Specifically, we consider adding mutable state and exceptions into the picture. We consider them separately and together, and I would claim that once we view them together, our base language forms the prototypical core of an industrial strength language like OCaml or Java. Furthermore, in the paper we also discuss how to relax the in-standard restriction. That is, so the predicate models no longer need to be perfect binary trees, and we can account for repeated queries, and we don't even need to query all the components of a point. We also consider how to extend the problem to search. That is, instead of returning the number of times the predicate was satisfied, return the points that satisfied the predicate. And we show that the same asymptotic bounds applies to the search problem. We also conduct an empirical evaluation. In summary, the takeaway is that control operators admit asymptotically more efficient implementations of some programs. And the intuition for why that is true is because control operators enable computation to be shared via backtracking. And as for future work, we would like to consider how linear handlers fits into the picture. So linear handlers are a special form of handlers that only allow the continuation to be invoked once. It is not clear that our current proof techniques would adapt readily to the situation with linear handlers, so it would be interesting to investigate. Another thing that would be interesting to investigate would be a richer type system, say one that features effect typing, and how that would impact the result. Thank you for tuning into my talk, and thank you for your attention.
So thank you, Daniel. If you want to join the authors for a live Q&A, again, you can just click on the link in the Slido room. All right, and now there's going to be a short pause, and when we come back, we'll have the next paper in session 2 of ICFP 2020. Hello and welcome back to ICFP 2020. And our next paper is going to be Computational Focusing, and it's going to be presented by Nicolas.
My name is Nick Ryu, and this talk is for the paper called Computation Focusing by myself and my advisor Steve Zdensowick at the University of Pennsylvania. Our paper is all about proving program equivalence. This is an important way of reasoning about them. So whether you have a compiler that performs CPS translations or just some optimizer that does function inlining, in order to justify them, you're probably going to want to be able to prove programs equivalent. The sort of gold standard of equivalence, the notion that we care most about, is called contextual equivalence. And two programs are contextually equivalent when they show the same behavior in all contexts. There's no way to distinguish between them. But proving this is difficult because there's so many different possible contexts that programs could be used in that we can't really just do a case analysis on all of them. So we need other techniques to prove equivalences, and the CIU theorem does this. It allows us to, rather than consider all possible general contexts, only look at evaluation contexts paired with closing substitutions. But there's still difficulties here, and in particular in call by value, there's still many possible evaluation contexts, so it's difficult to reason about the interaction between a term and its context. And call by name has this very similar dual problem. So another class of syntactic proof techniques includes logical relations and bisimulations. Logical relations in particular give you really nice high-level reasoning principles like relational parametricity. But there are still some limitations, and one of those limitations is that some equivalences between existential types have not been easy to prove in the past using logical relations. And the problem is essentially that logical relations are just more naturally used to reason about how a program produces an output than how it uses its input. So let's look at a particular value of this existential type. And let's look at how these values of this type are used. Well, we used existential types by pattern matching on them to unpack them, and here we unpack this existential into a function y, and this y is a higher order function, so we pass another function f as input into it. And f has the type x arrow x, but this x type is an abstract type, and so f must be the identity function. So with that in mind, let's look at these two values of the same existential type. They contain functions that themselves take another function as input, f. And they both apply f to many different values, checking to see that it does indeed behave as the identity function. Since we've already shown that this is true, we can look at the functions in these packages and confirm that they both are always going to return true no matter what. So in other words, this means that they must be equivalent. But logical relations and bisimulations struggle to prove this because they force you to come up with some relational interpretation for x that somehow relates values of Boolean type to values of integer type. But we have no such relation in mind here. There's not really a correspondence between values of x in one of these packages with values of x in the other package. So instead what we want to do is look at the possible context these values may be used in and exploit the fact that they're constrained by their types. So throughout the rest of the talk, we're going to look at a proof theoretic technique called focusing and show that that's actually useful for reasoning about programs. In fact, we can use that to prove this equivalence. Lastly, we'll see why this technique might be useful in compositional compiler correctness. For this talk, we're going to deal with a call by value language with predictive polymorphism in a pure setting, but the paper goes beyond some of these restrictions. So what is focusing? Well, focusing is a proof search technique that narrows down the search space when you're trying to find a proof of a certain proposition. And viewed through the lens of Curry-Howard, you can think of it as making things easier when we're trying to synthesize a program of a given type. So how does focusing narrow down the search space? Well, it does that by visiting fewer redundant terms that are just equivalent to each other via beta or eta laws. We don't have time to go into focusing in depth today, but I want to give you a flavor of what the focused terms look like. So let's try and visit all the focused programs of the Boolean to Boolean type. The first thing that focusing says we can do is apply the lambda type constructor anytime we have a function on the right-hand side. It says that just any term in our language of function type is going to be equivalent to some lambda. And that's true by eta in call by name, and in call by value we're also using normalization. But if you didn't have normalization, you could still use this technique. You would just have an extra non-terminating term to consider. So now we need to consider what the body of the lambda might be. And when we're trying to build that, focusing says that the first thing we can do is eagerly pattern match. Anytime there's something in the context that can be pattern matched on, focusing says we might as well do that pattern matching right now. There's no point in waiting until later. So now we know that all the terms we're interested in have a lambda on the outside and then immediately pattern match on its input. And what we're left to build are the two branches of the if statement. Both of these are closed because focusing knows that there's no point in pattern matching on x twice once we've already done it. And so we just need to build focused programs of Boolean type. And it turns out there are only two of those, true and false. And so we can use those to build our 4 candidate programs here. And it turns out that every function of Boolean to Boolean type needs to be equivalent to one of these 4 focused programs. We've cut out many non-focused programs, such as the identity function lambda x.x, but this program is still represented in the second bullet point here. So some properties of focused terms that to keep in mind are that focused terms are always beta eta normal. There's no way to beta reduce them, and they can't be eta expanded without introducing a redex. And we characterize them in our paper as a restricted type system. Basically, the usual type rules that you're used to, but restricted to be applied in a certain order. And this gives you strong inversion principles to do programmatic reasoning. Lastly, for every focused term, for every well-typed term, there's some equivalent focused term. This is called computational completeness, and it's the key property we need for reasoning about programs. And basically all it says is that we may have eliminated many redundant representations of the same program, but we haven't lost anything of value. There's still some representative focus program for any other program. So why are we talking about a proof search technique in a talk about contextual equivalence? Well, it turns out that a proof of contextual equivalence is just a search through all possible contexts, demonstrating the same behavior for each context. And so if you think about it like this and you apply the completeness of focusing, then you can see that there's no need to search through all possible contexts. You only need to search through focused contexts. So that leads us to a context lemma, which looks a little hairy, but all this is saying is that to prove two values equivalent, you only need to consider focused contexts, which are represented by a term nf with a whole x represented as a variable here. And if v1 and v2 are open, then you need to close them off with some closing substitutions, but you can assume that all the values in those substitutions are focused. So let's return to the equivalence that we wanted to prove earlier, and now we'll apply our focusing lemma. And this context lemma says, since these values are closed, we just need to consider some context nf and show that they both behave the same when the values are filled in for x. So what does the fact that nf is focused tell us? Well, the whole in nf, x, has existential type, and we know that existential types can be pattern matched on. So focusing says, let's do that right away. Now once we unpack the existential, we get this function y, and the rest of the body of the pattern matching statement gets to call y potentially. So there's really only two things that we can do here. Either we call y or we don't. And if we don't, then we can only return a constant Boolean value. So there are three possible shapes of programs here that this context may take. We need to show that the two values behave the same in each of them. This is easy in the case of the constant Boolean because the context just ignores its input. The interesting case is when we call y. And what happens here is that v1 is going to get destructed and substituted in for y. And it's going to get passed in f, which we've talked about before must be the identity function. So if you plug the identity function into the functions in v1 and v2 and you reduce, you can see that both of them return true. So what's left in the proof is to show that z is equal to true in both cases. And that, combined with a small detail about the proof structure that you can see in the paper, let us complete this proof. Now that we've seen program equivalence, let's look at compiler correctness. One property you might want about your compiler is that it preserves all of the abstractions in the source language. So to say this more precisely, you can say that two terms in the source language are equivalent implies that after you compile them, they should still be equivalent. To prove this, you need to consider an arbitrary source target language context, C prime, but we have a source language equivalence to use, so we need to back translate the target context C prime to a source language equivalence. And the key idea that focusing helps us with here is that we don't need to back translate every single possible target context, we only need to back translate the focused ones. There's a long history of using focusing in proof theory, but there's also related work here that uses focusing in the context of programming languages, especially as a guide to design features of programming languages. There's also work that uses focusing as a normalization procedure to decide the equivalence of terms in the simply typed lambda calculus. Lastly, normalization by evaluation is pretty relevant because it could be used to prove our completeness of focusing theorem. There are many different type system features and effects that we might study, and we expect focusing to be a useful tool along with all of these. In particular, the combination of linearity and focusing is really interesting to study because that's where focusing originated, and because linear lambda calculus terms have very nice normal forms that make them easy to reason about. To recap, our paper contributes a few things. First, we formulate focusing in a call-by-value language with predicative polymorphism, and we provide a proof of the computational completeness theorem. Then we prove a context lemma and show that that's useful in turn to prove various program equivalences like the one we saw today. Finally, we show that focusing can be used to prove compositional compiler correctness properties like full abstraction, and we do this for a simple compiler from a language that's pure into a language with a simple divergence effect that's tracked by an effect system. That's all for focusing for now. Thank you.
Right, so thank you, Nick. If you're interested in joining the authors of this paper for a live Q&A and you're in the New York time zone, then you can click on the link in the Clouder room. And now we're going to have a short break. Please come back and join us for the next paper in this session. So, welcome back to the second session of ICFP 2020. And our next paper is going to be Retrofitting Parallelism into OCaml, and it's going to be presented by K.C. Sivaramakrishnan.
Hi, I'm Casey, and I'm going to present our work on retrofitting parallelism onto OCaml. So OCaml is a reasonably popular programming language that is used by several notable industries, but also widely in the academia. OCaml language has particularly found favor for implementing software verification and static analysis tools, and also low latency system services. And for all of its strengths, OCaml is one of the few systems programming languages that lacks support for multicore. To that end, multicore OCaml is an ongoing project which aims to add native support for concurrency and parallelism in OCaml. Concurrency in multicore OCaml is added with the help of effect handlers, but the focus of this particular talk is going to be on parallelism. And in particular, we are going to look at the details of a multicore capable garbage collector that we have implemented for OCaml. The design space for multicore garbage collectors is quite wide. And what makes our work unique is that our design is guided by backwards compatibility concerns before parallel scalability. So adding parallelism to OCaml has several challenges. OCaml has millions of lines of code in production that have been written without explicit parallelism in mind. And this code tends to also use advanced features such as weak references, ephemerons, lazy values, and finalizers, which closely interact with the current GC. OCaml also exposes a low-level C API that allows the developers to write very efficient code, but also bakes in the GC invariants. And the cost of refactoring sequential code in order to work on a parallel runtime is quite prohibitive. So that is not something that we would want to do. OCaml is also a type-safe language. The addition of parallelism should not break type safety. For this, we directly borrow the memory model that was presented in the PLDA 2018 paper, Bounding Data Races in Space and Time, which guarantees not just type safety, but also other strong properties under data races. Developers using OCaml have come to love and embrace the low latency and predictable performance of OCaml. And this is thanks to the GC design. Stock OCaml garbage collector is a non-moving incremental mark and sweep GC, where new objects are allocated into a small minor heap by bump pointer allocation, and survivors are copied to the major heap. The major heap is collected with the incremental non-moving mark and sweep collector. At the start of a major cycle, there is a small idle phase, after which the roots are incrementally marked, followed by incrementally marking the rest of the heap. And once the marking is done, any unreachable objects are incrementally swept. And at the end of sweeping, we come to the end of a major cycle. This design has several nice properties. The allocations into the minor heap, which are majority of allocations, are quite fast, and we do not have any read barriers for reading OCaml object fields. And this design being incremental also leads to enviable tail latency performance. And while we add parallelism to this language, we would like to keep some of these nice properties still going. So we arrive at these following requirements for retrofitting parallelism onto OCaml. Firstly, we don't want serial programs to break on the parallel runtime. A well-typed serial program remains well-typed on the parallel runtime. And we also do not plan to provide separate modes for serial and parallel execution as Glasgow Haskell compiler does. This is because we want to reduce the burden of maintenance on the OCaml developers. Secondly, we want the performance of serial programs to be the same while running on the parallel runtime in terms of the running time, GC, pause times, and memory usage. And lastly, we want our parallel programs to remain responsive. And then we want the parallel programs to be able to scale with additional cores. We ordered the priorities this way because getting responsiveness is much harder than making our programs go faster. So with that, we design a multicore OCaml garbage collector. And our multicore aware allocator is based on the streamflow allocator, which uses thread local size segmented tree list for small objects and resorts to system alloc for large allocation. And the performance of this allocator is better than OCaml's first fit and next fit allocator, and is on par with the recent best fit allocator from OCaml. And the major heap is collected with the mostly concurrent non-moving mark and sweep collector based on the VCGC design. One nice aspect of this design is that we only need a very short barrier at the end of every major cycle. And I should at this point mention that domains are our units of parallelism. And in particular, there is no phase separation between marking and sweeping, and marking and sweeping phases between multiple domains may overlap. One of the major contributions in this paper is extending this design to support a variety of additional features such as weak references, ephemerons, 2 different kinds of finalizers, fibers, lazy values, and so on. Ephemerons are particularly tricky to get efficiently implemented in the concurrent multicore GC. Ephemerons themselves are generalization of weak references, and the property that they bring in is they introduce conjunction in the reachability property of OCam for objects in the heap. And this requires multiple rounds of ephemeron marking and also marking the heap in order to reach a fixed point. And in this work, what we've shown is we can implement a cycle delimited handshaking algorithm in order to perform the ephemeron marking without requiring a global barrier. The 2 different kinds of finalizers in OCaml also need 2 barriers, 1 barrier each. And in the worst case, we need 3 barriers per cycle, a major cycle. And because this design is quite tricky, we verified a model of this design in the spin model checker. Next, we come to the issue of what to do about minor GCs. Our initial design was based on Doliger-Leva 93 collector, which uses a minor heap per domain, but it's lazier on the lines of the GHC collector from Marlowe and Peyton-Jones 2011. So so this particular design has an invariant that there are no pointers between 2 minor heaps, and this allows each domain to be independently garbage collected. And unlike the original Doliger-Leva design, we allow pointers from the major to the minor heap. And the reason why we allow this is twofold. First, it prevents eager promotion, right? So early promotion is a problem where you point to an object which is promoted, which would otherwise have not been if you hadn't established this pointer. And this also mirrors the sequential behavior. And unfortunately, what this does is a particular domain may follow a pointer from the major to the minor heap to a remote minor heap. And this would break the invariant that we had. So what we instead do is insert a read barrier on reading OCaml object fields, which detects whether the result of the read is going to be a value in a remote minor heap, in which case the domain sends an interdomain interrupt requesting the target domain to promote the object, which in turn might perform a local minor garbage collection. And then the execution proceeds. Recall that I had mentioned that OCaml does not have read barriers, and now this design has introduced read barriers. So the first challenge is that we need these read barriers to be implemented efficiently for performance backwards compatibility. And in the paper, we show that we can do this with a clever bit of virtual memory mapping and a series of bit whittling tricks, using which we have brought down the read barrier to 3 x86 instructions. And a proof of correctness of this is available in the paper. And because these read faults are going to be so rare, the branch predictor correctly predicts the branch almost every read. So the performance impact of these additional instructions is minimal on sequential code. Unfortunately, though, the introduction of read barriers breaks the C API. Consider this example where we have 2 domains, each of which is reading a major heap object which points to the other domain. So at this point, this domain sends a promotion request to the other domain. So the 2 domains simultaneously send promotion requests. And in order to prevent deadlock and make progress, when a domain sends a promotion request, it has to keep servicing other promotion requests that it may receive. So the issue is that because promotion may involve a minor collection, a mutable read is in fact a GC safe point where GC may happen. But this breaks the invariant that we have in stock OCaml, where we don't have any read barriers at all. And in particular, the C API is often explicitly written with the knowledge of when a GC may happen. And introducing a read barrier where the read barrier is a GC safe point will require manually refactoring very tricky code. And this is unfortunate. So in order to get around this, we also implement a parallel minor collector, which does top the world parallel minor collection similar to GHC's minor collection. So this shows a timeline of the concurrent minor collector, where we have two domains, and the minor collections here can overlap with whatever activity is being done on the other domains. And in particular, we need a barrier once per major cycle. Whereas in the parallel minor collector, we need a barrier for two barriers for every minor collection in order to indicate the start and end. And these minor collections are very frequent. And in order to better utilize idle time while we are waiting for minor collections to complete, and when a particular domain has completed its minor collection but is waiting for other domains to complete the minor collections, we fill the slop space in the minor in the barrier with major slices. The advantage of this design is that we don't need read barriers anymore, but our global barriers are quite frequent now. So we need to be able to quickly bring all of the domains to a stop. So we insert pole points in our code for timely interrupt handling. And this is based on Feely's paper from '93. So the big question is, how does this perform? So we perform evaluation on a 2-socket 14-core Intel Xeon Gold CPU, where we've isolated 24 cores for performance evaluation. And we observe that the sequential throughput is comparable to OCaml. Compared to stock OCaml, concurrent minor was 4.9% slower and parallel minor was 3.5% slower. These overheads are quite reasonable. And the reason why concurrent minor is slower than parallel minor is the additional instructions for read barriers. But we also observe that both concurrent minor and parallel minor use much lower peak memory than stock OCaml. This is because our allocator is much more efficient in reducing fragmentation. So this gives us promise that we can relax the memory bounds in order to get better running times. And we also observe that our sequential GC pause times are on par with OCaml. These results and more details are available in the paper. Next, we look at parallel scalability. The graphs here show the scalability, the speed up of each of the benchmarks with respect to a sequential baseline. Overall, we see that the two variants perform similarly, except a few notable differences. On a few benchmarks, concurrent minor really suffers due to read faults, where just performing a read requires sending an interrupt, requesting the other domain to promote, that domain promotes, while the domain which read faulted is idly waiting. And we also see other cases where the unbalanced allocation leads to inopportune minor GCs in parallel minor, which causes scalability issues. We also observed that the parallel GC latency was roughly similar between parallel minor and concurrent minor. And in our minds, parallel minor wins over concurrent minor, because firstly, it doesn't break the C API, and it performs almost similarly up to 24 cores. And OCaml 5.0, which will have multi-core support, will use parallel minor. We may revisit concurrent minor later for a time when commodity machines will have lot of cores than they do now. I'll stop here. Thank you.
So thank you, Casey. And if you want to join the authors for a live Q&A, click on the link in Slido. Hello and welcome back to the second session for ICFP 2020. And the last paper in this session is going to be Liquid Information Flow Control, and it's going to be presented by Jean Yang and Nadia Polikarpova.
If you're the director of the FBI, you should be able to keep your social media accounts on lockdown. But this turned out not to be the case for former FBI Director James Comey. Journalist Ashley Feinberg discovered Comey's secret Instagram and Twitter simply by sending a follow request to Comey's son's private Instagram. The culprit? A leak in Instagram's suggestions algorithm. This kind of thing affects many more of us than just the Comeys, and it happens more and more every day.
Today's software handles a lot of sensitive information subject to complex security policies. Traditionally, programmers enforce these policies by storing policy enforcing code or policy checks throughout the application. It is all too easy to miss a check by mistake, causing a potential information leak. A much better approach is to let programmers specify policies declaratively and separately from the application code, and then let an information flow control framework ensure that the code satisfies these policies. IFC frameworks come in two flavors, static and dynamic, which have complementary strengths and weaknesses. In this work, we will focus on static techniques, which ensure absence of leaks once and for all at compile time, hence avoiding surprise failures and performance overhead at runtime. On the flip side, existing static techniques are unable to handle rich policies that modern applications need, or if they can, they require programmers to provide proof hints to verify absence of leaks. In this work, we developed a new IFC framework called LIFTY, short for Liquid Information Flow Types, which combines the best of static and dynamic techniques. LIFTY is a static framework, but unlike existing static solutions, it is able to verify rich security policies completely automatically. To enable this automatic verification, our first contribution is an encoding of IFC into a decidable type system based on liquid types, hence the name. Moreover, when the application code does not satisfy the policies, LIFTY can automatically generate leak patches that make the code provably secure. Our second contribution is a leak repair technique based on type-driven program synthesis. In the rest of this talk, I will first introduce our encoding of IFC into liquid types. I will then give a demo of what it's like to program in LIFTY, and finally, I will give an overview of how LIFTY's leak repair works. In the liquid type system, types are annotated with logical predicates called refinements. For example, this is how you would specify the type of natural numbers. By restricting refinements to decidable logics, liquid types provide fully automatic type checking of non-trivial program properties. But can we use refinement types to encode security policies? To answer this question, we draw inspiration from another line of prior work, security monads. In this approach, computations that manipulate sensitive data live inside a special monad, which we will refer to as TIO. For example, TIO int is the type of sensitive computations that return an integer. The purpose of the security monad is to keep track of the security level of the data that the computation manipulates and to disallow unsafe information flows. In LIFTY, the security level is recorded in the TIO type itself. Apart from the return type, TIO is parameterized by two refinement predicates, the input and the output label, which specify the security levels of the input and output effects of a TIO computation. More precisely, the input label specifies the set of users that are allowed to see the data read by this computation. The output label specifies the set of users who will see the data written by this computation. Both labels are predicates from the refinement logic and can refer to variables in scope as well as a special viewer variable. Now let's see how a Lefty programmer builds TIO computations. The building blocks of a TIO computation are atomic input and output actions that the programmer writes to model sources and sinks of sensitive data in the system. For example, if my program can access a shared key that belongs to Alice and Bob, I can give this action the following type. Here the input label specifies that the key is only visible to Alice and Bob, while the output label false guarantees that this computation will not perform any user-visible output. On the other hand, I can define an output action print that outputs a string to a given recipient. The output label of its type guarantees that only the intended recipient will see the string, while the input label true indicates that the return value unit is public. Good luck trying to hide a unit. Note that function types in Lefty can be dependent, so the label of the result can depend on the value of the argument. This allows Lefty programmers to encode rich security policies as types of TIO actions. Atomic actions are combined into computations using the TIO API that Lefty provides. The core of the API are the standard monadic primitives return and bind. Return simply wraps a pure value into a sensitive computation, and so its labels are trivial. The type of bind, on the other hand, is key to correctly tracking information flow in Lefty. Bind sequences two computations, x and y, such that the result of x flows into y. The type of bind is polymorphic in the labels of these actions, but not any four labels would do. To avoid leaks, we need to ensure that y only outputs to those users who are allowed to see the result of x. This is encoded by adding the input label I of x as a conjunct to the output label of y, essentially enforcing that y's output label is more restrictive than I. Finally, the input label of the sequence of x and y is the conjunction of their input labels, and the output label is the disjunction of their output labels. The TIO API has a third primitive operation for leak-free downgrading, which plays an important role in applications with rich policies, but I will skip its description in the interest of time. The TIO library also provides a range of convenient monadic combinators, for example map-m for mapping a sensitive computation over a list. Note that while the primitive operations are part of the trusted computing base, the derived operations are not. They are implemented in terms of a primitive operation and attached using Lefty itself. Now let's see how I can use Lefty to implement some simple functionality of a conference manager. Say I'm on the program committee of ICFP 20 and I'm viewing the list of all submissions. But I'm also an author of one of the submissions, highlighted in gray. As an author, I have a conflict with this submission. The conference manager has a policy that a conflicted reviewer is not supposed to learn the score or the decision for a paper until the notifications are out. Consider the following hypothetical but insidious leak that violates this policy. As a reviewer, I can sort the list of all submissions by their score. If the programmer is not careful, the sorting function might use the true hidden value of the score for my paper for ordering. In this case, even though the score is still masked, by looking at the position of my paper in the list, I can infer that the score is somewhere between 1.8 and 2.0, and hence the paper has likely been accepted. Yes! Let's see how Lefty would help us prevent this leak. To implement a conference manager in Lefty, I'll start by encoding the interface to the data store as a set of atomic TIO actions. For example, I'll add an action that retrieves a list of all submission IDs from the data store, an action that retrieves a paper title by its ID, and so on for each column of my submissions table. Now it's time to add policies. Recall that paper scores are restricted to users who are not conflicted with a paper, so I would like to change the input label of getPaperScore to reflect this policy. although the refinement logic does not allow mentioning program-level functions like getPaper conflicts inside labels. I can define an uninterpreted logic-level function, conflicts, that denotes the set of users conflicted with a given paper. I can now use this function to specify the desired policy on scores, that they're only visible to users who are not in the set of conflicts. To connect my logic-level function to the data I retrieve from the store, I will refine the result type of getPaper conflicts, stating that it retrieves exactly the same users as those denoted by conflicts. Finally, let's implement the sorting functionality. To this end, I will write a function sort papers by score that takes as input a data store DS and the current user client. Lifty supports a Haskell-like do notation that desugars into invocations of bind in a standard way. Here I first retrieve the list of all submissions, then sort them using a custom comparator that I will implement shortly, and finally project the paper titles and output them to the current user. Our custom comparator function retrieves the scores of the two papers from the store and compares them. I might not realize that the functionality I just implemented leaks information. After all, I'm only printing paper titles, which are public. Thankfully, Lifty is watching my back. If I ask to type check my program, it reports 2 policy violations for the 2 calls to getPaper score. Lifty is complaining that they're not visible to client. Instead of trying to decipher the error message and fix the leak myself, I can ask Lifty to do it for me. In this case, Lifty returns a modified program where either call to getPaper score is wrapped in a policy check. The check retrieves the conflicts list for this paper and checks whether client is on that list. If client is in fact conflicted, our generated patch returns a default score of 7. In the final part of the talk, let's see how Lifty's leak repair works under the hood. Consider a stripped-down version of the leak I just showed you. In this version, we simply retrieve the paper score and directly show it to the user, who, of course, might be conflicted. How does Lifty repair this leak? The key insight is to use the information from the failed type-checking attempt to localize the leak and infer a local specification for the patch. First, let's desugar the do notation into invocations of bind. While type-checking the program, Lifty infers the following types for the 2 computations sequenced by bind. Now recall that our type signature for bind enforces that the output label of the second computation be more restrictive than the input label of the first one. Hence, type-checking in this case reduces to the following implication between the labels. Lifty uses an SMT solver to validate this implication. In this case, the check fails and the program is deemed ill-typed. Lifty keeps track of which input action generated the right-hand side of the failed implication, so it knows exactly where the leak occurred. In this case, the problem is the call to getPaper score, whose result is too sensitive for its context. To fix the leak, Lifty replaces the offending input action with a patch template, whose intention is to return the original value whenever it's safe, and otherwise return a less sensitive default or redacted value. Crucially, the Lifty type checker not only pinpoints the input action that needs to be replaced, but also infers a local specification that the patch needs to satisfy in order for the program to be secure. In particular, the optimal input label for the patch is derived directly from the left-hand side of the failed implication. With the local specification at hand, we can use our prior work on type-driven program synthesis to fill in the holes in the patch, checking whether client is conflicted with the paper, and if so, returning 0. Thanks to the inferred local specification, synthesis is performed completely independently for each leak. So leak repair scales reasonably well to programs with multiple leaks, as we have seen in the demo. In conclusion, we have presented a new static IFC framework called Lifty. Lifty is able to statically and automatically verify applications against rich security policies and suggest leak patches when the application does not satisfy the policies. You can play with Lifty through a web interface available at this link.
So thank you, Jean and Nadia. There's going to be a live Q&A for this talk if you're in the New York time zone, and you can get to it as per usual by going to the link in Cloud. So now, if you'd like to join us for the virtual milling around outside the conference hall, chatting and drinking coffee, that would be great.
you